Hello and welcome everyone. My name is Eric Franzen, President of SemanticWeb.com. We would like to thank you for joining us today for this webinar, a joint production between Dataversity.net and SemanticWeb.com, with our speakers David Reed and Scott Van Buren of Blue Slate Solutions. Today, Dave and Scott will be discussing using semantic technology to drive Agile analytics. Just a couple of points to get us started. Due to the large number of people that attend these sessions, you will be muted during the webinar. For questions, we will be collecting them via the Q&A box in the lower right-hand quadrant of your screen. Or if you like to tweet, we encourage you to share highlights or questions via Twitter using hashtag SemanticWeb or our Twitter handle, SemanticWeb. As always, we will send a follow-up email within 2 business days containing links to the slides, the recording of this session, and additional information requested throughout the webinar. Now, let me get onto it and introduce you to our speakers for today, David Reed and Scott Van Buren. Dave leads Blue Slate's visioning for technical direction and innovation. Through his ongoing client delivery and tenacious interest in new technologies, he continually works to identify meaningful advancements in technology and delivery that will benefit their clients. Beyond maintaining a strong BPM focus, his key research and development areas are semantic technology, data security, and analytics. Scott is a senior consulting software engineer for Blue Slate Solutions. Scott has spent the last 13 years working in information technology and business consulting. His expertise is centered in database design, data warehousing, data analytics, reporting, and semantic technology. He leads both the data management and semantics centers of excellence, as well as leading the semantic technology aspect of Blue Slate's Innovation Lab. Recently, he has focused on designing ontologies and implementing data integration solutions for large healthcare players. And with that, I will give the floor to Dave to introduce today's webinar. David Reed, hello and welcome.
Well, thank you very much, Eric, and welcome everyone to our presentation here this afternoon or this morning, wherever you are. I'm David Reed, CTO at Blue Slate Solutions, and we're going to walk you through some interesting uses of semantic technology when it comes to analytics. So my role at Blue Slate is really to lead system architecture, data security, and our innovation lab.
Good afternoon or morning. I was on mute. I apologize. Wherever you may be, my name is Scott Van Buren, and I'm a senior consultant here at Blue Slate Solutions. And my focus, as was mentioned by Eric, is on the data side of the house, mainly in database design, warehousing, and semantic technology. All right, so let's take a look at what our webinar, the goal of this webinar is. Our goal is to demonstrate how semantic technology will enable you to make better decisions by providing the right data in the right form at the right time. What we plan on covering in this webinar or agenda is to introduce some semantic terminology just to level set you, give you a basis for the remainder of our presentation. Describe how semantic technology will simplify the data federation process, and present a case study analyzing post-discharge cost of care for heart attack patients in an attempt to illustrate how semantic technology and agile analytics can sometimes help us get to conclusions that were highly unexpected. So just so that we're all on the same page, let's take a quick moment just to define what we mean by data federation. What we mean by data federation is combining data from multiple independent data sources that may or may not be all either within or outside your organization. And this process of data federation, we believe, is a very iterative process, one that very closely mimics the process you go through when solving any analytics problem. And what I mean by that is we start by with defining an iteration goal or a goal of where we want to get to. What are we trying to, what is what we're trying to find out? And then from that goal we identify, okay, well, we need certain data. We need data to meet our goal, to get to the end result. So we define the data. Then we bring that data together, and as we said, we federate the data, so we're bringing it together from wherever that data may be located. And then we explore that data using analytic techniques or tools or whatever, and we end up with a final result. Now, at this point, we determine, did this give us what we had expected? Is there more we need to know? You know, what else is there that we might have added to this to get a better, more refined result? So we determine what that is, and then we redefine our next iterative goal. So as you can see, this is very, very closely mimicking the analysis process that we go through, or the cyclical process or iterative process that we go to every single time we solve any sort of analytic problem. And we believe that this is the key reason that semantic technology and the agility that data federation provides can really help us. So let's take a brief high-level look at semantic technology and how it enables the Agile data federation process. What is semantic technology? Well, semantic technology has been around for over 15 years, very much on the web side of things. There are a number of tools that have existed for over 5 that are created by, you know, a lot of large manufacturers, Oracle, IBM, to name a few. There's also many, many other commercial offerings out there from other companies as well. It's based on, or semantic technology is based on a number of well-defined standards from the W3C, or World Wide Web Consortium, that define both the languages that represent the data in semantic technology as well as the query language. So there's ontologies. That's the representation of the actual data, or how we're allowed to model the data or represent the data. There are triple stores, and this is analogous to the database on a relational side of the house. And you'll see later why the triple stores is the naming convention used. And then there's a language, Sparkle, which is utilized to query the data. Sparkle is analogous to SQL on the relational side of things, and in actuality is very similar to SQL, looks in a lot of ways like SQL. And anything you pretty much can do in SQL, you can do in Sparkle. But there's one thing about Sparkle that really indicates and jumps out at you to say that, you know, semantic technology was designed for this data federation process, and that's the fact that federation, or the bringing together of disparate data sources, is assumed within the language itself. There's actually, you have the ability within a Sparkle query to define multiple endpoints and bring that data from those different endpoints together within the same query to get to work within your result. There's also one added feature to semantic technology that is extremely powerful and helps us with this Agile data federation process in many ways, and that's the idea of inferencing. What inferencing allows you to do is allows you to take the asserted facts that you've asserted in your ontology or your triple store, or the data that you've actually put into there, and it allows you to infer additional facts from that data by the use of things called reasoners, which work on a number of algorithms to utilize that data to come out with other facts that can be inferred from what you've stated. And that's a very, very powerful tool. So what's different about semantic technology? Well, we've already talked about the fact that, you know, inferencing and reasoners is somewhat different. But another key difference with semantic technology than other data storage methods is the fact that in semantic technology, the majority of the structure is logical, not physical. Now, when we think about a relational database, you think about, you know, schemas, tables, columns, things that are extremely physical, and whenever we modify the data, need to be modified or restructured or refactored. In semantic technology, there's really only one entity within the technology that would be considered in any way physical, and that would be the way that each data fact or data assertion is represented, and these are represented in what we would call triples. And as the name specifies, you'll see why they're called triples. Now I'm going to get into some terminology I'm going to use here to describe this structure. Don't get hung up on that, because I'm going to give an example shortly thereafter that will clearly define what it is we're talking about. But anyway, a triple is comprised of, as it sounds, 3 different pieces. We have a subject, which is just a piece of data. Think of it as a piece of data. We have a predicate, which is that subject's relationship to another piece of data, an object. So as you can see, it's comprised of 3 parts. That's where the name triple comes from. And these 3 parts comprise every data assertion that we make within to what we call our triple store. So let's take a look at an example. We have Lisa, who's a piece of data or an entity. And she has a relationship. She's the bio mother of Michael. So there's our asserted fact. It's a triple comprising of 1 asserted data fact about Lisa, and she's the bio mother of Michael. Now, we can add additional facts to this over and over and over, and together these facts will comprise what we call as a directed graph. And this is one edge of that directed graph we're looking at here. So we can simply just add, as we come across additional facts, we can add additional triples to our data. So Lisa's favorite sport is bowling. We just simply, it's an independent assertion. It stands on its own, and we've added it to the data, and we've had to change nothing as far as structure. We can add Michael as a friend of Carl. We simply just add that fact. Again, it's independent. Nothing regarding the rest of the data had to change, as well as the structure. So as you can see, we can add relationships very, very easily. But in the same way that we can add relationships, it's just as simple to remove relationships. And these assertions can be added and removed as we prove or disprove them throughout whatever process we're working through. So if you think of this from the analytics standpoint, I mean, it's what you go through when you do analytics. You start with a set of correlated assertions or, data points and assumptions. And then you go through iterations of the process and you disprove some existing assumptions or pieces of information, and you add additional information along the way. So as we can see here, say we went through an iteration of our process, our federation process, and we determined that when we got to our end where we came up with a result, we realized that, well, we came across that there's an additional fact that we know about Lisa. She has a favorite drink, iced tea. So we want to add that to our data. So we simply just assert the triple, Lisa, subject, favorite drink, predicate, iced tea, object. And we just add that to our triple store. No change of any other structure or the rest of the data that's within our database or triple store. But just like that, we also realized along the way that, okay, well, Lisa, we made a mistake. Lisa didn't really have a favorite sport. So we want to remove that. We don't want to skew any results or queries that we run or analysis that we do, and we just simply remove that fact. So we just get rid of that 1 triple. It's removed from the data, and nothing else has to change. So you can see the power and the flexibility of semantic technology and how this might be really, really useful when we're working through analytic problems and trying to bring together data along the way. So let's take a quick look at an example and bring it down to some more real-world terminology and a more real-world example. We're going to take a look here at a healthcare example, and the reason we used healthcare was that we assumed that pretty much everybody has been to the doctor or dealt with some kind of healthcare claim or whatever, and would have some familiarity with what we were talking about. So we're looking here at a healthcare payer, an insurance payer, the insurance side of the business where the provider submits their claims to them for payment. And these payers have 2 systems. In this case, what we're talking about, 2 separate, standalone systems or independent systems that we're bringing together that we want to utilize for our analysis. And those 2 systems are a claim system and a provider system, right? And they're totally separate systems. So we determine what data we're looking to gather from these systems, and we bring that data down, or we transfer that data down into triples. And this is done normally in an automated fashion. So we end up with claims or instances of a given claim type, and we end up with instances of a given provider type. So what you see here is, think of these instances as rows in a relational table. That's what they would be analogous to, as rows in a relational table. And each of these instances or rows have data attributes or column values, right, related to them. And in this case, you'll see we simply add all of these different entities, instances as well as data attributes. We're just adding triples. In the case of the instances, we have claim 1. The triple would be claim 1 type source claim. And in the case of provider, provider 1 type source provider, etc. And then in the case of adding data, we have claim 1, the predicate is ID, and then the data, the literal data value that ID relates to. So we add all our different attributes that we're interested in based on our initial pass through the iteration, right? So we determine that our first pass through our goal requires certain data, and this is the data that we choose that we want from there. So we model that data out and bring that down into triples on the source side. We also know that, and it's not shown here, we didn't depict it just for easeability of viewing this, but there's a relationship between claims and providers, right? A claim has a provider based on a foreign key between claim and provider on the source side of things. So we have to represent that with triples so that we keep that relationship. So we end up with this relationship or predicate of provider, and then instance claim 1 has provider, provider 1. And we relate them together just like you would relate them in tables. So now we're going to get into what we call the target domain or business domain. And I just want to make sure everybody's clear that although I'm showing these in sequence, that we go from one to the other, these two domains are really, source and target, are really something that can be handled in parallel. And in actuality, you don't really want your target domain to be skewed in any way from your source. So you want to represent on the target side of things, or the business domain, the way you view the business from a user side of things, so that you understand the terms, you understand the concepts, you understand the entities that exist from the way you understand the business. So in that case, or in this case I should say, we've determined after we looked at our business domain, totally separate from our source domain, that our world is really comprised of claim headers, claim lines, and providers. So we create triples, or we start to create our domain or model it in an ontology on the target domain side. And we end up creating instances of these things that, that mimic the instances on the source side. And we create the relationships between the entities, same as we did on the source side, but in this case we're doing it from the domain. So we know that these instances, these claim header instances that we create, have line numbers or lines on the claim. So we create the relationships between each line that represents a given claim header, and it's just simply another triple. Claim header 1, line, relationship or predicate, claim line 1. And we do the same thing between claim lines and providers, because that's where we see this provider relationship is taking place, is we see it taking place between the claim line and providers. So we create that relationship with it more triples asserted between the different instances. And then we assert our data attributes from our domain side. And you can see that although in this case our data attributes match up for the example, we have the same number, you can create your domain and there could be many, many more attributes that you come up with that you aren't even going to use in this case, but they would exist. We just don't show that here. And you'll also notice that all of our entities on the target domain side of things are the way we want to name them. They're a claim header, we understand what that is. Our IDs, or claim ID is claim ID. So you'll notice they don't mimic or match the names on the source side of things, which is really powerful because when we do any sort of analysis or when we do any sort of reporting from our domain side of things, we'll simply be able to always refer to the entities and the names the way we see them, and the data will come across in that manner. So anything that we generate initially can just be reused over and over again, regardless of how the data changes on the source side of things, as long as the mappings are the same to the same entities. So all we simply do to bring the data over, now that we have the two sides of things, we have the source side defined, we have the target side defined, is we just simply create these same as or equivalent relationships. Again, another triple stating between the attributes on the target side and the attribute that's being represented by that attribute on the source side, or that's the same as the attribute on the source side. We just simply create a triple. Claim ID, same as ID, or equivalent to ID. And what that allows us to do is now get the data from the source side into our attributes on the domain side, just by creating that relationship. They're now looked at as being one and the same. And we can do this for all of our data attributes that we choose to utilize. And just as we can create these very simply, we can simply remove that triple that relates them, and we can break that relationship, and that data will no longer come over to the target side. So let's say we got through an iteration, as we've been talking about. We've gotten to the end of our iteration, and we've came to what the result is. And we determine we don't like the result. We determine there's one more piece of information we think we need. And that's data service. Well, we simply add that on the source side. We represent it on the source side, and we bring that data into triples. We add an entity on the target side for each and every instance, an attribute, if you will, which is another relationship called serveDate, that we then can bridge to the source side, as we said, or create that mapping or that same as relationship to the source side. And we now have serveDate in our data. So for the next, we can now utilize that in our new result and come up and determine if there's anything additional that we need to do or add. So you can see that the power of semantic technology makes this federation or bringing together of data sources very, very powerful, very agile. So let's take a more real-world look at some data here. And what we're looking at here is a commercial tool that actually does exist. It's called Gruff, and it's by Franz Incorporated. This is one, it allows you to, in a visual way, view these directed graphs and the data within these graphs, which is really nice. It has a lot of other features as well, which we won't cover. But it's really nice at manipulating and dealing with your data from a visual standpoint. So what we have here is we have a claim header entity, right, a type, and then we have a bunch of instances of these claim headers. And what we're going to do is we're going to look at specifically at claim header 5, just so you can see how this data starts to come together and view it and what the graph looks like when we put it together. So there's our claim header 5. And claim header 5 has an amount billed, which is a piece of data. You know, it's a triple relationship with a literal value, as we've seen. So all we would need to do to assert that is claim header 5, amount billed 7,500. We have a provider identifier, and same idea. We would just create the triple claim header 5 provider identifier and its literal value. And there are many other data facts asserted about claim header 5. And we can assert as many more as we would like by just adding triples to the triple store. And we can remove any one of these facts and at any time we would like by just simply removing that triple from our data. But like claim header can have data, literal data values, it can also have relationships with other entities, like we were seeing in the prior example in the prior slide, where we had claim headers having claim lines. Well, in this case, claim header has claim lines. And you'll see the relationship is has claim line, and it's a relationship between two entities, claim header 5 and claim line 3. And claim line 3 has data about it, and each of those are separate triples asserted off of claim line 3. And claim header 5 also has relationships with member 4. Okay, so it has a beneficiary, and that beneficiary is a member, and that member is member 4. Member 4 has its data, and then member 4 itself can have relationships with other entities. In this case, member 4 has a member address too. So all we simply do is assert member 4 has member address 2, and that member 4 has that member address. And we can now, we query the data, we would find that member address for that member. And member address 2 has a number of, literal data values about it, or pieces of data about it that are asserted using triples as well. And just like we can add this member address 2 by a simple assertion of member 4 has member address 2, we can remove that member address by just simply getting rid of that triple that states member 4 has member address 2. And now member address 2 can still exist, but it is no longer related with member 4. And if we end up with another member address that we need to relate to member 4, we can simply create that entity, add its attributes, and then create that relationship between member 4 and the new member address. So all of this data that you see here is a result of federating together two independent claim systems, or two disparate claim systems. And this is what you end up with when you bring these relational structures down into what we showed you and go through the mapping process. You end up creating one unified view of both of those data sources. And the nice thing is that you can do this in iterations, in pieces, as opposed to what we call boil the ocean method. and doing it all at once and having to determine up front everything that I think I need and bring it over now. We can bring over little at a time, and we can work our way into exactly what we need. So let's take one more look that'll help maybe solidify this idea. So here we have claim header 110. And claim header 110 is just an instance. It's one of those claim header instances that we saw. And it's comprised, when we're all said and done going through the federation process, of attributes and data from both of those sources that we saw. And now when we go and we look at that from the domain side, we simply can query that as if it's part of what we understand the domain to be, and it ends up being a unified view of these individuals as opposed to data coming from two different sources, as opposed to staggered, instances of part of the data here and a part of the data there, and trying to understand how that data fits together.
Great. Well, thank you, Scott. So what we'd like to do now is walk you through a case study where we apply these techniques that Scott has shown us and carry out an analytic exercise. And we're going to stay in the healthcare space because hopefully that terminology makes some sense to each of us who have been to doctors and seen claims and things of that nature. So in this case, our case study is based on a healthcare plan, so a payer, and this is a payer that pays Medicare claims. So this is a company that is contracted by Medicare to take care of administering the claim payments and the relationships with the providers, with the doctors and the facilities. Now, the hypothesis, the issue that this plan wants to focus on is that they believe that there are inconsistent treatment plans being created for heart attack patients. So someone goes into the hospital having presented with a heart attack, they're admitted to the hospital, and eventually they're discharged from the hospital. And the belief is that the plan of recovery that that patient goes through differs, and there are different costs and outcomes associated with that. And so this contractor, this payer, would like to understand if, in fact, there's an opportunity to optimize the post-discharge planning so that there's a good process that leads to good outcomes, as well as reducing the overall cost to the Medicare Trust Fund. So we're going to want to go through a process, as Scott described, where we iteratively figure out whether there's evidence of this situation occurring, and if so, can we identify a root cause. Our infrastructure is very basic for this example. We've got a Part A claim system. Part A claims in the Medicare space are, you can think of as your inpatient claims. So these are the claims that come in after someone has been in a hospital. We also have a Part B claim system, and these would be the claims for outpatient type services going to a primary care physician or a cardiologist, or things that happen after the patient is discharged. And you notice both of those systems have what we call headers and lines. And these are just the data structures that record the fact that there's a claim, and it has some high-level information, the patient's name and which hospital they were in, et cetera. And then the lines are the individual procedures that they went through, things of that nature. So there's a one-to-many between the headers and lines. And then finally, there's a couple of other ancillary systems that deal with storing data about beneficiaries, the patients, essentially, as well as the providers, the doctors and facilities. And then a medical review system. In the case of paying claims, these companies, these payer organizations, typically will have a medical review department that looks at a subset of the claims going through to verify that, in fact, they should be paid, that they're filled out appropriately, that it's for things that are covered, and so forth. And so there's a system that manages that data. So that's our infrastructure at a high level. The schemas, we're not going to go into a lot of detail, but just to show in our simplified view, the schemas are really for the Part A and Part B. We have our header and line tables. And for providers and beneficiaries, we just have very simple tables, really header level detail for our providers and members. And then we have a medical review system that just keeps track of when the request for documentation went out to the provider, when the information was received, and the information about the adjudication, was the claim, paid or denied. Now, thinking back to the process that Scott walked us through, we talked about the fact that we really want this to be an agile process. We want to be able to get at this fast. We want to learn quickly whether or not there's a reason to advance this, whether we need more information and so forth, take advantage of this agility that semantic technology gives us. So we're going to start by defining that iteration goal that Scott referred to. And in this case, we just want to know whether there's evidence that the overall cost of those Part B claims, so the post-discharge process, is there evidence that there's different costs associated with that based on the patient? And you'll see here that we talk about these DRG 280, 281, and 282. The DRG is a diagnosis-related grouping, and that's used by Medicare to essentially price the claim to figure out how much they should be reimbursing the provider for that claim. And a code of 280, 281, and 282 are all associated with individuals who are discharged from the hospital having had a heart attack. 280 would indicate that the patient was very sick. They had other complications and comorbidity conditions. Maybe they're a diabetic or something of that nature. And when you get to the 282 code, that means that there was really nothing else wrong with them other than they had this heart attack. But otherwise, they're fairly healthy people. And that comes on the Part A claim side. So that's information we're going to need out of the Part A system. And so if we look at the specific data that we want from Part A, we're going to need the patient ID and that DRG code to figure out what is the subset of people that have had heart attacks. We're going to also need the admit and discharge date so we can get an idea of length of stay in the hospital, and then how much was paid, because our purpose here is to figure out whether there's evidence that there are different costs associated with these patients. On the Part B side, at this point, we're just interested in costs across all the episode of care around the rehabilitation of the individual. So thinking back to Scott talking about the capabilities of semantics, we need to have an environment that supports those features. So Scott talked about we need an ontology, so we'll need to create one that just has that data in it that we talked about, that knows about Part A claims with patients and discharge dates, and Part B claims with costs. It doesn't need a lot of detail, just that little bit of information. We'll need a place to house this data that can be done in memory, or it can be an actual physical triple store. We need that reasoner that Scott talked about because that supplies a lot of the power that allows us to connect this data. So where Scott showed the mapping between the source domain and the business domain, we're using the reasoner to help with those connections and inferring those relationships. And then finally, we need a way to get to this data, and that's that Sparkle query language that Scott mentioned, and we'll need an endpoint that we can actually query. We'll also need whatever analytic tools we normally use. It could be that you're a SaaS shop, you've got SAS installed, maybe you're doing reporting, you're using BI tools of some type, or it could be use open source solutions like R, but we're still going to need analytic tools. The semantic environment doesn't do the analysis for us, it simply makes it easier for us to bring the right data together at the right time, in the right format, so that we can then focus on the problem that we're trying to solve rather than on how to bring the data together. Now on the source system side, we just need the headers out of the Part A claim system and the headers out of the Part B claim system. And using that process Scott showed us, we're just going to connect those few pieces of data into our semantic environment. We're going to end up with triples that we can then query into our analytic tools. So given that, this is an example of a query that we might execute. This is the actual part of a Sparkle query. And what's nice about this query is that in this one query, we're actually bringing the data from those two different source systems, the Part A and the Part B system, are being brought together in this one query. And we can just focus on that business domain side of things. So the terminology that we're using here and the relationships that we're referring to within the query are all based on the business domain and have nothing to do with the physical structures, the relational structures on the back end. And so we can write this query to say, please bring me back for each patient the total costs of the episode of care as well as the Part A costs and the date ranges where they were in the hospital. And I don't have to worry about on the back end what exactly had to be brought together and joined in order to accomplish that. Now looking at what we might see from doing that, this is a box plot. So if you're not familiar with this from statistics, essentially this just shows us the range of the values that we're seeing. So we're looking at the total episode of care cost. So this is the Part A cost and the Part B cost. And the box shows us essentially the 25th to the 75th percentile of values, and the solid black line in the middle of the box is the 50th percentile value. And then the little circles up above are outliers. So they are way outside a couple of standard deviations typically, indicating that we have some claims that appear to have vastly different costs than the bulk of the claims that we're looking at. Now that's by DRG. We can also look at this by length of stay in the hospital. So this lower chart is actually by length of stay. Those are number of days the patient was in the hospital. And what we can see is that the same pattern exists. Obviously, it costs more if you're in the hospital longer, so we see those box plots showing the box higher up, and the median costs are higher. But the outliers exist in all of them. So one of the things that we learned really quickly is the outliers don't seem to have anything to do with how sick the patient was or how long they were in the hospital. And we'll look at that one other way to see if that, in fact, is true. Another way we can look at this data with simple statistical approach is just to plot the cost of each claim, the total episode of care cost for each claim. And we do that. Column 1 are the DRG 280s. These are the sickest patients. So these are people with a heart attack, but also other conditions, diabetes. Maybe they've had some kind of stroke or something of that nature. The 2.0 column are the DRG 281s, and the 3.0 column is the DRG 282. So those are the healthiest patients. And what we can see is that there are outliers in all cases. So the outliers aren't explained by the DRG, or essentially how sick the patient was, and it also has appeared that it's not explained away by the length of stay. Now, we can go look at this by Part A and Part B to see if we can figure out where these outliers are coming from. The Part A costs appear all grouped together. We don't see any outliers there as we plot the cost of these claims, so Part A doesn't seem to explain it. And if we do the same thing for the Part B costs, we do see that those outliers seem to be explained by Part B. But we also notice on the Part B side that there seem to be a couple of stratifications of costs as we plot those claims out. And we're going to want to understand probably what's driving that differentiation. We can also do the same evaluation by length of stay, and here we don't, again, see anything interesting. We have outliers in all cases. We have some overlap with costs based on the length of stay, which isn't too surprising, but essentially we see that pattern. The longer you're in the hospital, the more it costs. And we can plot that for Part A separately, and we see the outliers go away. And we can plot that for Part B, and we see that's where the outliers are coming from. So we seem to have confirmed that the outliers are being driven by the Part B costs, which supports our hypothesis that it's the post-discharge process that seems to be affecting cost differentiation. And we've also shown that it isn't the length of stay or necessarily how sick the patient was going into the hospital that seems to be influencing these cost deviations. So going back to that iterative process, we've gotten to a result where we've proven to ourselves that, yes, there's something here. There are cost differences, and now we need to come up with a new goal for this iteration. And really what we want to get at is what's the root cause behind these cost stratifications? What's driving that? And if you recall, Part B costs are the claims that are part of outpatient care. So this is going to primary care physicians, cardiologists, pharmacologists. Any of those types of visits would likely come in as a Part B claim. So those costs are being driven by the patient going to these different types of facilities and different types of providers. So we're going to want to look at the providers, we want to look at the facilities, and the relative order that the patient is visiting those to understand what exactly is happening post-discharge. The data we're going to need to support that is to understand how much was paid for each claim on the Part B side and the type of provider. So we're going to have to bring in a little more data. So this is the picture of what we were bringing into our environment. And now what we're going to do is we're going to add the Part B claim lines, because now we need detail around every process, every procedure and type of provider that the patient went to and facility. And we're also going to bring in, from the general info, the provider information, because that's where we're going to get the detail around what type of provider, what specialty of provider. And on the semantic environment side, we are going to need to broaden that ontology by adding these new pieces of information and account for the fact that we have this line level data for the Part B claims, we have this provider detail. So as Scott showed us, it's very simple to add a few more concepts to our ontology. Nothing else has to change. The rest of the relationships stay intact, and we just add a few more, and we'll then have access to that data. An example of a query that we might run in this case, once we've done that, is to simply say, show me every claim that has come in on the Part B side for every patient. And again, the power of this query is that it is essentially going out and federating the data from now 3 different systems. We have our Part A claim system, our Part B claim system, and our provider system. And that data is being brought together, and this query is referring to things using the terminology of our business domain. So the business user or the data scientist isn't worried about what the back-end systems called things or what the column names were in those environments, which can be different from system to system. And they concentrate on the business definitions, that business ontology that's been created. And so we bring that information back. And one way we might want to look at that is using a flow diagram. And if you haven't seen a flow diagram before, they're fairly straightforward. I'll walk you through quickly how to read one. You read it horizontally from left to right. And the very first position is showing us the facility or provider type of the first claim that came in. And then the second position would show us the second claim facility or provider type. And the third one would show us the third, and so on and so forth. And we continue to read this off to the right. Now, vertically, what it is showing us is what type of provider or facility. And in this case, we have an inpatient pipe facility. This is a rehabilitation hospital. We have a cardiologist as another possible first claim to see. And the third type that we typically see is a primary care physician. The height of the box is telling us what percentage, if you will, the number of patients who went down this track. So most patients post-discharge from a heart attack first go and visit their primary care physician. Another group, maybe around 30% based on the size of that box, go to a cardiologist, and a very small fraction end up having to go into some kind of rehabilitation facility. They're not ready to directly go home. And so this is by patient count. We can also look at this across all the DRGs. This happens to be DRG 282. These are our healthiest patients, but we can also look across the other DRGs. And the pattern is fairly similar. There's just a shift in how many patients go to which type of provider or facility. But we don't have to just look at this by patient count, which is how this is mapped out. We can also think of looking at this as accrued cost. So if we consider the fact that the inpatient facility, the number of individuals who come out of the hospital after the heart attack and go into a rehabilitation facility is fairly small, as we saw, right? That box is fairly small compared to the cardiologist box below and the primary care physician one below that. But if we look at the aggregated costs, so the mean costs of a patient through the process, the rehabilitation process, that inpatient step adds a lot of cost up front. So that box is actually very big, much bigger than the other two, because the cost of going into an inpatient facility is high. The other thing that we need to consider is what that does overall is it makes that patient look very expensive. At the end of the process, that patient who ends up at a cardiologist managing their care has a very expensive process they've gone through compared to someone who had their care also managed by a cardiologist but didn't start in an inpatient facility. Now, if as we work through this exercise, what was determined was, well, we can't really control whether a patient needs to go into a rehabilitation facility. If they're not ready to go home, they have to go into one of these facilities. And that doesn't really affect our study. We can't just say we're going to change the process and not have them go to such a facility. What it does say is that another study could go off and look at whether there are things that could be done either when the patient arrived in the ER initially or as they were a patient in the hospital that has some kind of impact on whether or not they get discharged to this type of facility. But that would be a separate study. So a decision was made in this case to remove those claims from this study, and we can see here that it skews the cost greatly if someone goes into the rehabilitation hospital. So looking back at those box plots that we originally had, we see those outliers, and if we take out the rehabilitation hospitals, we see the outliers go away. So that lower plot has those claims removed. And we can do the same thing looking at the data by just spreading it out and plotting it on this chart. And again, we can look at Part A, and here's Part B, and the outliers are gone, but we still have some kind of stratification going on that we're going to want to look at. And again, the flows, again, the rehabilitation hospital's gone, and all we really notice is that the sicker the patients are in the hospital, the more likely their care is to be managed by a cardiologist. That's about the only pattern we see here. Looking by cost, we can determine from this that if care is managed by a cardiologist, it appears that that in fact is a more expensive route than if the care is managed by a primary care physician. And you might figure that that would be true. Cardiologists would likely be a more expensive specialty than a primary care physician. and so that this outcome probably isn't particularly surprising. However, what's great about having experts looking at data, so our subject matter experts looking at data in this fashion, is it allows them to start to spot things that they might not have seen otherwise. And in this case, what the medical review nurse spotted was the fact that there were claims in here that were being shown in this model that was being built that actually shouldn't be paid. When this data was created, these claims would have been paid, but over time, through the medical review process, these claims, it was determined, were excessive, either too many visits to the doctor or what have you. And so we actually need to get those out of our model because they're skewing our model. And we can see here that, yes, the primary care physician managing the process, it appears that that is less expensive. But we do need a third iteration because we found this situation where we have claims counted that shouldn't be. And so in the third iteration, we're going to want to remove those claims. And what we need to do that is the information from the medical review system, the adjudication status and claim information. So again, this is what we've brought together. We're going to add a fourth system, the medical review system, with the adjudication and the claim detail. And on the semantic environment side, we're just going to broaden that ontology again. So as Scott showed us, we're going to add some more of those relationships within the business domain and bring that data in. Again, we don't have to refactor anything. We don't have to recreate any data structures for the other information. That will work just as it always has. If we do that and now remove those claims that we shouldn't have, what we see in the lower plot is that we've brought the costs are lower overall. Not surprising. They're now claims that we've removed because they should have been denied. And if we plot the overall costs, again, looking at Part A, nothing interesting. And on the Part B side, we still see a couple of cost stratifications. So there are at least two apparently different processes that lead to different costs. And again, looking at the flow diagrams, and the lower chart looking at the mean aggregated cost, we can now see something very interesting. If the care is managed by a cardiologist, it actually requires fewer visits to any type of facility or doctor for the patient to go through that recovery process. It also is less expensive. The size of the box we can see is smaller, and I'll show that on a histogram in a moment. And the primary care physician managed process in general, so again, these are all averages, and there's a lot of data brought together, but in general has more steps and adds up to more cost. And here we can just look at a simple histogram of that and see that the cardiologist managed care was actually less expensive overall than the primary care physician managed cost. Now, I will say that this study is based on an area of the country for a payer and isn't something that could be then generalized across any situation. This is completely based on the facilities available and the practices that are followed in those areas. So to wrap this up, hopefully what we've shown you is how semantic technology supports data federation agility, why it makes it rather straightforward to bring information in and remove information very quickly. And that really allows us to accelerate the data analysis process because data analysis really needs the ability to quickly decide what data to bring together and how to relate it. This allows experts to then go down an unexpected path and ask for a new piece of data without requiring us to go through a lot of extra work to bring that new piece of data in. It's very hard to predict up front what data is going to be useful in a study, and we tend to end up either not bringing in enough data, so we miss something because we didn't know we were going to need it, or we end up trying to bring in too much, that boil the ocean approach where we try to federate a lot of data because we think people might want it, and we end up wasting effort. It takes a lot of time. There's a lot of overhead to that, and this allows us to avoid that part of the process. Another advantage is that we can really target the federation at the analytic study we're going after, and that makes it much more lightweight in terms of the information we have to bring together and the relationships we have to create within that data. And then finally, the way that we see this being used longer term is that this allows us to create a data warehouse, the design for a warehouse or a data mart, because it creates a way for the business to work with data, figure out what's valuable to them, what they're actually going to use, and starts to support an ROI around building a larger solution, applying that data. We really appreciate the fact that you spent an hour listening to us and hope that you saw some interesting insights, got some interesting insights from it. And we're going to turn it back over to Eric now for some Q&A.
Dave and Scott, thank you so much. Really, really interesting stuff. We will open up the Q&A at this point. We have a lot of good questions already, but we also have some room for some more. We have about 10 minutes that we will use with that. First, we'll start off with our single most popular question ever for every webinar, and that is, are the slides for this going to be available? I happen to know the answer to that. Yes, they will be available. The slides and the recording we will post at SemanticWeb.com within 2 business days. Everyone who registered for this in advance will get an email within 2 business days with links to all of that material. Now on to the stuff that I can't answer. So David and Scott, listen up. The first question that we have, is it possible to validate the semantic model following the addition of new triples to confirm the model was not damaged?
Yes, this is Dave. I'm gonna guess by not damaged, we mean that we didn't somehow corrupt data, that we aren't misrepresenting the source data. And yes, actually, one of the things that we can do is we can create within the process, and in fact we do this, create within the process some kind of checksums that say we expect X number of claims, or the total number of dollars for this subset of DRGs was X. We should still see that over on the federated side. So there are things that we absolutely would want to do to validate that we haven't corrupted or biased or lost data, that the fidelity of the data has been maintained as we went through the process. So it's a great question, because you are changing the representation, the structure, and you do want to make sure that that process is doing it with high fidelity.
And because your talk covered aspects of semantic technology that improve analytics, one person has asked, in your experience, are there categories or use cases of analytics which are very difficult or even impossible to do without semantic technology?
Yeah, this is Scott. Probably the most difficult thing to deal with as far as analytics is dealing with data that comes from an external source. Some third-party source or some public source that potentially in semantics can be available online or out on the interwebs to access, and through a normal analytic process or normal analytic methods, it's difficult to utilize that data without bringing it all in-house or having some way to get at it or having them put it in a format that you can utilize it. With semantic technology, it's just as easy as you're federating in a source from internal data sources. You can federate a third-party source. As long as you can access where that data resides, you can easily get that data in-house and utilize it without having to bring in all of that data to your side of things.
And we have a couple of questions here about tools. One person is curious which reasoner you used. Was it something included with a Allegrograph?
Yeah, actually we use different reasoners. A lot of times the federation step is doing very basic reasoning. You're not using some of the more esoteric OWL capabilities if you're familiar with web ontology language and some of the interesting things you can do. So most of the reasoners, things built into Oracle, certainly mentioned Allegrograph, but even if you're doing a smaller project and using open source solutions, Sesame and Jenna or Pellet, things like that absolutely can do a lot of this basic data federation before you have to start spending a lot of money to deal with a bigger solution.
Yeah, the other tool question we had was about the visualization that you showed. I think you mentioned Gruff, but what was the name of the tool that was being used to generate the visual representation of data?
A lot of the slides that we showed here were done using R. A lot of this analysis was done on the R platform.
Okay. The person who originally asked about the data and is there a way to check the model is clarifying that he was actually more concerned about the ontology rather than the data described by the ontology. So is it possible to validate the ontology following the addition of new triples. Confirm. I think it's more of a structural concern. You know, they want to be sure that the model was not corrupted rather than the data itself.
Right. I get it. This is Scott. Ways to validate that, I mean, as long as you assert triples into your model that are valid based on the standards, right? I mean, you pretty much can change your model in any manner and there's not going to be any sort of error per se. So the recommendation that we use, or the thing that we generally do, is we have a lot of queries that we use to do checks against that. So when we add data or remove data, that we expect certain results, and if those results don't return, then we realize we probably broke something. Because more than likely you're asserting facts that you expect are going to end up resulting in something in particular, and you can write a query to find that. Also, if you're using a tool like Gruff, you can even visualize it. You can even put it up on the screen and look at it in a visual manner so that you can see what you just did to the data as well.
Do either of you have any information on performance on large data sets? This questioner says, it looks like a lot of overhead. How is this managed?
Yeah, actually, this technology scales really well. And so you have a few options. Certainly there are commercial platforms, Oracle clearly, Allegrograph from Franz, Stardog. You know, there are platforms that really have had a lot of work done to tune them, to make them run really fast, run queries really fast, make it load data really fast. So depending on the problem that you're trying to solve, what we've found is that sometimes we can do the queries against the back-end systems more or less in real time and federate that data into an in-memory triple store. It's somewhat common when doing analytic work that you don't actually want the ocean of data. You actually want a sampled subset anyway, because you're dealing with bias or some population's overrepresented or what have you. So there's quite often it's only a subset of data that you want to pull for a sample, and so you tend to be reducing things down into tens or hundreds of megabytes and not gigabytes and terabytes. But if you're up in gigabytes and terabytes of stuff that you're trying to federate and run queries against and analyze, you're more likely going to need one of these commercial solutions to actually bring the data into a physical triple store that can then optimize from there.
Sure. Is there any common technique to automatically determine the relationships between the various pieces of data?
Well, if we're talking from a generated side, we generally use an automated process to just use the metadata that is existing within the, within the structure we're pulling the data from, to generate relationships to represent the source side of things. So if you're dealing with a database, there's all kinds of metadata behind the scenes. You can utilize data types, column names, tables, that kind of thing, and those can be represented directly into triples. So you can pull that structure directly from your source. When it comes to representing your target, that's pretty much the way you say things relating, right? So if you think a piece of data is related to a specific entity and you model it that way and that's the way you want to see it, well then when you bring the data over, that's how it will be represented. So pretty much how you see it is how you represent it when it comes to the target side.
Okay, and we have time for one more here. Can you tell us more about the technology for linking existing systems to a semantic database? Briefly.
Yeah, there are. The basic technique is not complicated. What's powerful, what's cool about a directed graph is it is an incredibly flexible data structure, and relational databases are fairly limited, and it's trivial really to represent the data structures from a relational database in a graph. And so the tooling to do that, the representation to do that is straightforward. We have built a tool that we use when we do this work for clients. We call it Data Unleashed, and it actually inspects the metadata like Scott was talking about, and just creates those triples, the metadata triples and the extracted data triples as well. We can also do that by federating queries in real time. So we can either pull the data out into a triple store or we can federate it in real time. But the technique is not complicated, largely because the directed graph is so flexible.
All right. Anything you care to add, Scott, or?
No, that pretty much summed it up.
All right. Thank you, Dave. Thank you, Scott, for this great presentation and Q&A. I'm afraid that is all the time we have for today. Just to remind everyone, we will be posting the recorded webinar and slides to SemanticWeb.com within 2 business days, and I will send out a follow-up email to let you know the links and other requested information. Also, don't miss your chance to meet Dave and Scott in person at the 2014 Semantic Technology and Business Conference. That's taking place August 19th through 21st in San Jose, California. They will be giving a half-day tutorial on integrating data using semantic technology, so a much deeper dive into some of the topics we looked at today. Thank you again for attending today's webinar, and I hope you have a great day. Thanks, Dave and Scott.
Thank you.
Thank you very much.